All right, so um, some announcements. There's another ICA coming up that'll be due ICA C1. So I think that's before lecture C1. I'm trying to think. I think we have a B3, so they're going to be due from a week from today, but I have to double check that. But bigger thing is the homework B1 is available. This is an individual assignment. It will be due relatively soon. Next week. There is an extra credit opportunity at the end of it if you're interested in that. This is preferably typed and electronically formatted, so it's legible and easy for the grader to grade. It goes along with the kind of communication component of this course. When if you hired an engineering firm, you're going to be submitting a lot of reports. You frequently will be using Microsoft Word. If you're thinking about going to grad school in engineering, you'll be using LaTeX. So, either of those two technologies, be good things to practice on here. Try to have things be kind of concise and clear and legible, and if the grader can't read them, then they'll have to mark off for them. So, and also kind of organized in sort of the order that matches the assignment. So a couple clarifications or hints. So this is kind of similar to what we've been talking about for question one. I'm expecting at least two examples of each category. So we've talked about this before. If you're having trouble thinking of, for example, two types of entities, think about breaking them up. And so if, animal is your entity, you could say, well, actually, there's four types of entities here: dog, cat, bird, human, that I could use instead of just animal. Similarly, if it's an airplane, you could just have a passenger, but then you can think, well, there's actually different types of passengers, and those might be different types of entities. So I can break that up into priority, business, economy, and so on. So that's something to think about for question two, where you're going to be doing a hand simulation. If you go to table 3.2 in the textbook, which is linked, you can have access to it, is linked from Canvas, then you'll see definitions for all of the variables used in that example. But this is just a quick summary of that. Is that LQ, that's the number of customers currently waiting for service. LS is the number of customers currently being serviced. So the total number of customers is the currently in the system is the sum of these two. In D, that is a cumulative statistic, so it's not a state variable. That's the number of customers who have departed the system by that time. So it just keeps rising. Similarly, S, seems like a strange one, but that is a sum of the response times. And so we have this term response time, which is the sum of the time that you took waiting plus your time actually being served. So it is the total time for a customer or an entity in the system. That is a response time. And S in the table is the sum of those response times over time. So that will keep growing. And the reason that we have this S is because if we divide by the number of departed customers, then in D, then we can get an average response time. So that's an example. If you're doing one of these sims, you might have these cumulative statistics because you're going to create these averages at the end. So that's why we're doing this weird thing. We're adding up time. That is just so you could eventually calculate an average. And then finally, this one is the more complicated one, F. This is going to be less than in D, but this is the number of departed customers who have spent 5 minutes or more in the system. So when a customer departs, one of the logic things that you're going to do on a departure event is you're always going to increase in D, but you're only going to increase F, which is going to be another whole number. You're only going to increase F if the customer was in the system totally for more than 5 minutes. That doesn't mean their service time is more than 5 minutes. Their service time may have been 2 minutes, but if they waited for an additional 3 minutes or more, then this F will end up increasing. So that's kind of the trick here, is that I think I ended up double clicking there, but is that in D, let's see if I can get back the little pointer. Oh, well, we'll do that. In D is always going to increase by 1 whenever someone departs. F may increase by 1 if that person spent more than 5 minutes. Otherwise, it won't change. S will always increase, but it'll increase by a variable amount of time depending on how long they spent in the system. So response time is just, again, the difference between the departure time minus the arrival time. That's the big reason why you have to keep track of arrival time, because when they depart, you need to know when they arrive so you can calculate that response time. That's why arrival time is an attribute on these entities. And then, like I said, the response time duration is the sum of the delay waiting plus the duration. But if you keep track of their arrival time, then it's easy to calculate that. So let me just see if I can again double click on this. There we go. I think that gets me back to where. Okay. All right. So that's clarifications in question 2. Are there any questions about that before I move on? And so for sanity check, those should be properties that you see, like LQ plus LS. Those should always add to the total number of customers currently in the system. ND should always increase. F should always be less than ND, but will be increasing. Doesn't have to increase, but it's non-decreasing. So I guess ND and F are both non-decreasing. And then S is also non-decreasing. And it's not numerically related to these two, but whenever ND increases, then S is likely to increase as well. Okay. In question 2, the missing leading interarrival duration is not a mistake. So you'll notice at the top, I give you, I forget, I think 4 interarrival durations and 5 service durations. And so sometimes the question is like, well, isn't it a one-to-one core? Like, doesn't every entity, every customer have both an interarrival time and a service? And the first one does not, because the first customer arrives at time 0. So they don't have an interarrival time. So that's the reason why really you shouldn't view the interarrival times and service times as being married together. It's almost like the service times do ride along with the customers, but the interarrival times are in between the customers. So if there's 5 customers, each one of them has a service time, but there's 4 gaps in between them. And the interarrival times go with the gaps. So it's not a mistake that there's one less interarrival time than a service time. Okay. So any questions about that? Does that make sense? We're going to do an example where you see that in action. And then question 2, again, these are sanity checks. I've mentioned some of these already, but the future event list, which is another name for the event calendar, it will always have exactly one arrival event. So we talked about last time that whenever you process an arrival, before you move on to the next event, you have to schedule the next arrival. So that means that in the future event list, there will always be exactly one arrival. There will never be 0 arrivals. There will never be 2 arrivals. There will always be exactly one. So if you see more than one or less than one arrival in your future event list, then somewhere your hand simulation logic has gone wrong. There will be no more than one departure event. There's only one server in the system, so only one entity can be being serviced at a time. So there can only be one departure scheduled in the future. There might be 0 departures because you might be waiting for entities to arrive, but there will never be more than one departure. And then the clock time must always match the time in the first event record. And so what I mean by that is, so that as we walk from event to event to event, the previous event you processed had an event calendar whose first event was the time in the next row of the simulation trajectory or execution. So if you're at time 7, if you go back to the previous time, its future event record list should list time 7 as the next event in the list. So that's another thing that will always be the case. I mentioned LS plus LQ must always equal the total number of customers in the system, in the checkout line. And LS, the number of, because we only have one server, you can only be serving one entity at a time. So LS will always either be 0 or 1. LQ could be anything, but LS will always be either 0 or 1. The cumulative statistics always non-decreasing. F will always be less than ND. Response times jumps in S will be larger than the corresponding service duration because of the wait times. So all of this I mentioned before. And then the answers question 2 should be consistent with information in the bonus. So if you do the bonus, which is basically take your hand simulation and then code it in Excel so that in Excel in one shot will calculate everything, the answers that you get in the coded solution in Excel should match the answers that you've done by hand. So that's another sanity check. Okay, so any questions? Let's see if okay, that got one away. All right. Again, I'll mention the arena competition. I'm not going to say much about this because we talked about this last time. But if you're interested in this kind of extra extrinsic motivation for your final project, that is maybe a little more challenging, but also has the potential of a prize payoff, then application forms are due end of September. I think I might have forgot to say this last time. I said it before. I think the application fee per group is like $20 or something like that. Sky in the past, I think we've got a pot of money where we can help cover that $20 per group. So if you let me know, I can get, if you're interested in this and you want to enter this competition associated with this course, then I can connect you with our business office and they can reimburse you for the entry fees. Likely reimburse you for the entry fees. I can't promise someone else's money, but that is the intent. And then likewise, there's FlexSim, but you won't be able to get as much support from this class. But it is a perfectly fine discrete event system simulation tool. It just doesn't have to be the exact tool that we're using in the class. The class will give you insights into how to use FlexSim. Just you'll have to figure out some of the smaller details yourself. If you're more interested in the FlexSim competition, which is more healthcare oriented, that's totally fine too. Likewise, if you want to check out the Simio competition, Simio is another big competitor to Arena. That's fine. So we're not, just forcing you to use Arena if you're interested in these competitions, if one of these resonates more with you than the others. Questions about that? And I do have this up, so in case there's any anonymous questions if you wanted to come through. All right, so from last time, we're trying to get more and more comfortable with these distinctions. So people said after Tuesday's lecture, they asked the lab TA if they could have an extension, and lab TA thought that was a good idea, so chatted with me and gave you an extension on that lab report. I think it's a Friday night, so that you can help use the info that you picked up Tuesday and today to go towards that lab submission. So if we think about a crosswalk system here, there's a lot of stuff going on. So it'd be interesting to sort of think about what are the resources, what are the entities, and so on. So you can see here that these cars and this bike are waiting, and anything that waits like that is likely an entity. And you could say, well, then what is it waiting on? Well, they're waiting for access to this bit of road. So this bit of road with a crosswalk, that's a resource. And it's a limited resource once there are people in it. So right now, this couple that is walking across, they have exclusive access to that resource. So none of the traffic going down the road can get access to the crosswalk. So they just have to wait. So we're seeing here that when we look at the system, we can start seeing who is waiting, what are they waiting on. Once you start filling in these blanks, what's an entity and what's a resource should just pop out. And so here, hopefully it becomes a little clear that we've got different types of entities. People arriving to the crosswalk are entities, bicyclists arriving to the crosswalk are entities, cars arriving to the crosswalk are entities. The crosswalk itself is a resource. And so the time, the activities, what's the average time it takes for someone to walk across a crosswalk? That's an activity. Once someone enters the crosswalk, we can say it takes roughly 30 seconds to get across a crosswalk. Some people do it faster, some people do it slower, but I can go out and measure that without having to simulate with the time of day or whatever. Any time of day, it's going to be roughly the same distribution of time to get across that crosswalk. For people, it'll probably be between 25 and 35 seconds, so some distribution. And then for the cars, it might be between 5 and 10 seconds, some distribution. So whenever either one of these gains access to that, it is preventing others from getting access to it. And then how long is it preventing others? That's that activity duration. And so, and then then the events? Well, if you already know what the entities are, you already know what the activities are, the events are the things at the boundaries of the activities. So an activity is like someone's crossing the crosswalk. Well, the events are someone entered the crosswalk, that's an event. Someone left the crosswalk, that's an event. A car entered the crosswalk area, that's an event. A car left the crosswalk area, that's an event. A car arrives to this waiting area, that's an event. So that's, hopefully when you look at these pictures, you just start seeing those categories and it just starts falling out naturally. And a great way to start seeing that, a great lens to look, on the microscope that is the engineering brain that's looking at this system, is who's waiting and why are they waiting? And if you start with that story, everything else should just unroll. Question. It's a great question. So when we talk about the boundary of the system, we need to sort of say, what do we need to put into our simulation model? And is there a way to put it in there? And if we did find a way to put it in there, would it change anything? So these signs, at the most kind of proximate level, don't have really any way to be implemented in the sim. But you could say, but what is their effect? Their effect might be that based on the size of those signs, it might change how quickly these cars see, like how far away they have to be before they start changing the way they're approaching it. So if they're big flashing signs or whatever, then maybe from a cars from very far off will start slowing down. Whereas if they're small signs, if the crosswalk isn't very conspicuous, maybe it's going over a hill, then maybe they won't slow down until the very end. So that might change your arrival dynamics. So in that case, not all of the spatial stuff necessarily will be built in a direct way, but they might have indirect effects on your activity durations, for example. If we were doing an agent-based model where now the motion isn't governed by a process distribution, it's governed by what the agents see, the sort of, as the ethologists would say, the umwelt of the vehicles, the sensory and perceptual experience of the vehicles. In that case, you would then need to model how far out can this car see and what can it see? And at that point, you'd say, well, if this car can see 3 meters out, whenever a sign becomes in that 3-meter bubble, then the car needs to respond appropriately, in which case then modeling exactly where the sign is was really important. So for things like an agent-based model, those spatial details are more important than the process model, where those details end up sort of factoring themselves in to things like activity durations. Okay. Any other questions about that? I think I've got some of these things summarized here. So in case you didn't get all that down, this is how I would model the system. There are 3 interacting processes. I'm using that word process here. Processes are opportunities for entities and resources to meet. And those are cars on roads, bikes on roads and bike paths, pedestrians on sidewalks. So in each one of those processes, there is a common resource. So in Arena, we might have 3 different boxes that will all be different places where these entities and resource meet. But when you drill down into each box, they'll all use the same resource. So if the resource is being used in one box, it won't be able to be used in another box. And so that's a way that when you draw things out in Arena, you can draw things in parallel. So on the diagram, they don't look like they interact. But when you drill down into those rectangular process blocks, you find out that all of those blocks are connected. It's almost like they're one big process. So the cars are entities, the bikes are entities, the pedestrians are entities. These roads, bike paths, sidewalks, those are kind of the processes. There's a well understood pattern, so that's what we mean by a process. And the process generates these entities and they compete for these resources. And so the common resource here is this road segment. So entities from multiple processes compete for this crosswalk area. Activities generally include waiting for them to arrive and waiting for them to leave. So that's the hidden activity here is the interarrival duration. So, how often do they arrive? Well, we model the how often, like what time in between, that's another activity. So it's another thing we're kind of waiting on the next arrival. So it's sort of summarizing there. So any questions about that? It's just a breakdown of what I was just saying, kind of in more words. Okay. So our generic example of this MM1Q single server, which has its own service rate. So this mu here is sort of the average time it takes to serve a customer. And this lambda is the average arrival rate. So 1 over lambda would be the average time in between every customer. And so we say entities here are those that are waiting for the resources. So we're saying that, again, where is the waiting? Well, the things that are lining up here are waiting for access to this thing. This is the limited thing here. This is the unlimited thing here. The unlimited thing typically are the entities. The limited thing typically are the resources. The thing that's limited that hangs around forever, well, that whatever it does when an entity interacts with it, that is the activity. Activities are the things that take time. So waiting for another arrival, if there's nobody in line, that's an activity. And then performing the service will take a certain amount of time to do the service. So that's an activity. Delays occur because of misalignment of activities. So if it takes you 10 minutes to do a service, but you only wait 1 minute on average between every entity, then that means that entities are going to have to wait because they just don't line things up just right. So our goal as operations researchers is to take the things that the environment gives us that we don't have any control over, like maybe the service time, unless we might be able to say, can you train your workers a different way that reduces their service time? Maybe that's one recommendation we can make. But if that is just not possible, then we could say, well, we can't really control the arrival rate. In fact, that might only get worse with advertising and things like that. We might be able to analyze the effect of an increased arrival rate or decreased arrival rate. But given that this is fixed, the environment gives us that, and the environment basically gives us that, then how do we rebuild the process so that we can get a better alignment of activities so that you get less delay generated? That's our job when we build these models. All right, so let's practice some of that. So, I've got a couple of different scenarios here. So let's say the research question, the operations research question we're interested in is finding out how long does each container take to reach its destination. So again, I've got, let's imagine that we've got this facility here where we can load and unload these container ships, and then we've got containers and then stuff in those containers. So once they get loaded on the ships and the ships go through their shipping lanes, they arrive somewhere else, and then they get unloaded in a similar sort of facility. So we can focus on different research questions. And by focusing on different research questions in this system, we'll get different choices of entities and resources. So if we're focusing here on the question, how long does each container take to reach its destination, then we're modeling this as containers are the things flowing through the system, and they're being delayed by ships that carry them. So based on this, then what is a container? Is it an entity or a resource? Entity. So I guess I could have done clicker. How many people say entity? How many people say resource? All right, good. Entity. It's the thing that is waiting. So the container is the entity. And the ships, then, that's what they're waiting on. So a container can't go anywhere if there's no ship. So we would model the ships, the availability of the ships, as potentially resources. Now, we could maybe come up with a complex model where you need to have two types of entities arrive at the same time. So you've got ships arriving via one process, and they have to wait until they're full, and then entities arrive, and they have to wait until there's a ship to be put on. And then once that ship is loaded up, then it goes off. And if we're studying how long the ship had to wait, there's ways in which we can think about that. But if it's something that is focusing on a single port, and we're just really interested in, say, how long does it take to load a ship up, then we're probably going to have the containers as the entities and the ships that are the resources. And then the ports we don't actually model. So this is like the example or the question about the signs in that example. The ports are abstracted away into the activity. So there's a lot of stuff going on the ports. We don't have to model all of that. All we need to know is how long does it take on average, or what's the distribution of time? If a container is ready to get loaded, and there's no containers in front of it, how long is it going to take for that container to get on that ship? Is it going to take 30 minutes, 20 minutes, 10 minutes? Is there a distribution of time? And if we know that distribution for every container, if we've got 1,000 containers, then we can say, okay, how long is it going to take for those 1,000 containers to get loaded onto ships? And and once the ships are each loaded up, then how long do we have to wait for the next ship to come? And then eventually we can figure out, okay, for every 1,000 containers, it's going to take 3 days for all of them to clear or something like that. So, but all of those details of actually picking up the container, moving it around, whatever, those are abstracted away in the beauty of stochastic modeling into that distribution. So we don't care about all those fine scale details. So questions about that example? Is that's sort of clear? All right, so then we can flip to a different question. What is the longest duration a ship will stay at one port while loading and unloading? So now, same system, we have containers being loaded onto ships, but we make the ships the entities because ships are being delayed by activities at the ports. So now the loading of each container is performed by the port. The containers and the ships together are entities, and the ports are the resources. So this is kind of that example where I was saying, if we're backing up and only focusing on how long the containers have to wait, containers are just the entities. But now, if we start asking questions about the ships, usually the thing you're asking questions about are often the things that are good candidates for entities. Now, you can ask about resource utilization. So in a medical office, how often, have I staffed too many doctors? And if I have a 10% utilization of my doctors, maybe I don't need to staff as many doctors. That's a type of question you would ask about your resource. But if you're asking, a lot of the questions you'd be asking about delays and things like that would often indicate that those things you're asking about are best modeled as entities. And so for this model, where I'm saying, I don't know how many ships there are, I just know ships arrive and they need to get loaded up, and their arrival rate could differ. And if the arrival rate of the ships matters, they probably should be entities. So if ships arrive very, very quickly, then ships are going to sit there waiting for the port resources in order to even start loading containers. And so in that case, the ship probably has to be the entity. But if we just assume that there's already a ship there, and we want to say, how long does the containers take to get on to some ship, and I don't care about how frequently the ships arrive, then in that case, maybe the ship can be pushed into the port resources and not be made an entity. So it all depends on the question that you're asking. So for this question, I would try to model this as containers and ships being different types of entities, the ports being the resources that joins these entities together when they're both available, and the loading of each container is an activity performed by the port, and all of these details get washed away in the distributions that I choose. So any questions about that? These are just modeling choices. You could make other choices and you might get better or worse models. The question is sort of like, ultimately, have we built a model that is insightful and is efficient to run? And if your model keeps track of too many things, then maybe you're not going to be able to get your 100 replications in of this model. And that would be bad if you need that level of statistical power. Then the other question, will opening a new canal increase the total number of ships? So now I'm zooming out and looking at the network as a whole, not just the port. And so as I zoom out, you should imagine that a lot of the fine scale details that I was modeling in the previous question get sort of blended away into these distributions. So now I'm looking at ships are the entities to be counted. I'm not even really talking about containers anymore because the ships are already loaded up with containers. Why would I keep track of all the individual containers? They're not going to change the answer to these questions. Maybe knowing how heavy the ships are but that could be an attribute that I could model on each ship that, this ship happens to be loaded up with this many containers, this ship loaded up with this many. I don't actually care about the arrival and departure of the containers. Those are just properties of the ship at that point. So the ships are the entities. The ports and canals are two types of resources. So the ships can be delayed. Like what are different things that can delay a ship from getting on its way? Loading up at a port can delay a ship, but also getting through a canal where only one ship can fit through at a time. So now the canals become a new type of resource. And the canal operation, as well as the container handling, are different activities that just get put into an activity duration. So on average, it takes a ship 3 hours to get through this canal and all the locks or whatever. Sometimes it's less, sometimes it's more. If someone else is using a lock or the whole canal, maybe the ships just have to queue outside the canal. And so they just have to wait there, and that generates waiting time. Then if they have to go to a port, then those ships, before they can go on their route, they have to stop at that port, and they may have to wait on another ship that is using that port. But all of the details about the containers, so containers were very explicitly modeled in the last two examples, but in this case, we're not worried about the containers. So it's all driven like, just like that example that was asked about the firefighters last Tuesday, or earlier this week. The same system, you can choose different entities and different resources depending on what question you're asking. So are there any questions about this? Do those examples make sense? The different choices of entities and resources. And once you've fixed your entities and resources, then it should naturally make the activities fall into place. Like the activity has to be consistent with your resources. Okay. All right, so we talked about this last time. Entities usually are moving, but they're almost definitely moving in the sim. They don't actually have to be moving in the real world system. So, we talked about, like, we think about, this a general process of an entity arriving and an entity leaving, then there are different ways that can happen. And so a vacuum cleaner is, in most models, going to be a resource because it is the limited thing that in order to clean the entire floor, the vacuum cleaner has to hit every portion of the floor. And so we don't actually think of the vacuum cleaner as an entity because it's always there. But we think about stuff on the floor as the entities that, as the vacuum cleaner moves around, it generates arrivals. So it is the movement of the vacuum cleaner that generates the arrivals, not the movement of the entities. Normally, entities move. I mean, in most models that we're going to build, entities move, but they don't have to move. There can be other processes generating those arrivals. So it's the arrival rate that you really have to focus on. You could say, like rather than is it moving or not, what is arriving and what process is generating that arrival? And if it's, and you could say it's easier for me to model this as arriving at a particular rate, even if they're not moving. So you have to kind of decouple. The proximate mechanism of the arrivals is the vacuum cleaner moving around. But from the vacuum cleaner's perspective, it's sensory, it's its own umwelt, then it, as far as it's concerned, dirt is arriving to it, as opposed to it arriving to the dirt. So that's just kind of what we're saying here. So questions about any of that? All our basics of choosing entities, resources, activities. Okay, and then we did this example. We're going to do more examples, so I'm not going to step through this in great detail here. But last time, I gave you an example of a car wash, and we sort of said that, given that we know when the first car arrives and we have a way to figure out when the second car arrives, and given that we know how long the first car will take to get through the wash and to do the vacuum once it gets there, and we have a way to figure out how long the second car will take to get through the wash and go through the vacuum, then we should be able to generate this series of events just by unrolling logic. And that's what we did last time. We said, well, the first thing we do is you'll do in your homework, and this is the new part, is you'd say, we only care about the simulation up to the simulation endpoint in your homework. I say the simulation ends at whatever, 21 seconds or something, or 21 minutes. I give you a number. And so the very first thing you do is put that in your event calendar, put that in your future event list. That is not a real event. It's not an event that comes from the real system, that comes from the constraints on the sim. So the sim only wants to run to this point. You just throw that in there and then forget about it. Then that just naturally handles the ending for you. Forget that it is an end, just treat it as an event, and then process as an end once you get there. But otherwise, forget that it's an end. And then you just go and you start. You know, the logic is you schedule the first arrival at time 0, and then you push through the logic. And we're going to step through a more detailed example of this. But you know, this is what we did last time. So we jump to events, schedule new events, jump to those new events, and so on. And as we do that, then there's going to be times where there are delays that accumulate. So these are times when an entity arrives, but the service that it's waiting for is busy. And so it has to queue up. And so we have to create state variables to keep track of how many entities are queuing up at the time. And how long they're in the queue, that is that delay that accumulates. And then eventually they jump and schedule, and we keep doing that process over and over again until we can build that whole timeline. So that's what we did last time on Tuesday. So you can go back and review that. We're going to again do another example of that that is much more like your homework example here, I think today. So that's why I'm not going to go through that whole example again. But that's just a reminder of where we left off. So any questions? Okay, so let's do an iClicker example here, which probably means I'll have to escape out of here. Man, really? All right, so let's I'll do a short answer, I suppose. Where question is uh, um, that what type of resource is the thing that is delayed? I guess so that if I'm describing a system, what is the best? And I tell you that in this particular system, these objects are being delayed, and so they're being prevented from going on their way. That it is best to call those entities, resources, or something else. So the things that are being delayed, the things that are trying to move through a system but are getting stopped at particular points where they have to wait, are those better as entities, resources, or something else? I'll wait for that just a second here. And then I think if I'm come on, clicker. All right. Well, I'll just leave that up for a little longer here. So this is going to be very similar to your homework. So we're basically going to do an example almost identical to your homework assignment. I mean, different numbers and slightly less complexity, your homework assignment. We're basically go through the steps here. So if you haven't looked at homework B1 yet, then what basically I give you an end time. I say you're going to simulate this up to some time, 21, 19, 15, it says there at the top of the assignment. And then I give you a table that looks like this one. And so I say there's going to be a certain number of customers, theoretically unlimited, but I'll give you enough that you won't run out of customers before. If you do the sim right, you won't run out of customers. So that's another trick or tip, sanity check. And then underneath that, I'll give you a list of interarrival durations and a list of service durations. And I format them like this, but again, it's probably better to think of the interarrival durations being in between the customers, not associated with the customers. So this 4 means there's 4 minutes between these customers. This 2 means there's 2 minutes between these customers. This 1 minute, this 9 minutes. I'm using all whole numbers here just to make it easier, but in a real sim, these would be real numbers. These would be non-negative real numbers. And they would probably be drawn from a random distribution that we would then model the parameters of. But in this case, we haven't gotten there yet, so I'm just giving you the numbers. And then service durations, and then these are associated with these customers. So for whatever reason, this customer is going to take 1 minute when they get to the server. This customer will take 8 minutes when they get to the server. This customer will take 1 minute when they get to the server, and so on. These service durations are all activities. They are not wait times. They do not include how much time they're waiting in the queue. That's what you get out of the sim after you run it. These are once they get to the server, how long is it going to take? So I give you these, and I basically say, and assume that the first customer has no interarrival, so the time 0 is the first customer's arrival, and then generate the simulation execution. Hand simulate the table of every time in the simulation, so you can see what delays are generated per customer. And that's what we're going to do here. So the state variables that we care about, that we're going to calculate at every time step, because again, state variables, every time step will represent an event that happened. An event is the one thing that potentially can change state variables. So at every time we generate a new event, we have to check every state variable to see if it changed. And the state variables we keep track of are the number of customers waiting for service in the queue. So that will be any number from 0 to infinity. The number of customers in a server. In this system, not in all systems, but in this system, we have one server and it has capacity 1. So that's why this LS can only be 0 or 1. It's either the server is idle or busy. If we had a server that had more capacity, this LS could be larger. But for this example, it's either 0 or 1. And then we have cumulative statistics, like I talked about in the hints for the homework, the number of departed, and I'm not going to worry about F for this example, but you have F on your homework. So the number of customers who've departed at that particular time that we've simulated, and the total response time, where response time is the difference between their departure time and their arrival time, which is their total time in the system. Service time plus the wait time. So customer 3's response time will be at least 1, because it'll be 1 plus how long they waited in the queue, which we don't know ahead of time. That's why it's an output. These are inputs. We know them ahead of time. We know them before we even run the sim. That's what makes them inputs. But the delays, we have no idea. We need to actually simulate the system to get those delays. That's why they're outputs. So each customer, we're putting into a data structure where in order for us to calculate that response time, we have to keep track of every customer's arrival time. So this is in a real system, you wouldn't have this. Or if you were analyzing data, you might look at video or whatever and try to keep track of, oh, that person, they left. Let's go back and see when they arrived. But in our system, we have a Post-it note that we can smack on every customer as they come in and say, you arrived at this time. And then when they leave, we can pull that Post-it note off of them. And then we can say, whatever the current time is, minus that Post-it note, that's how long they were in our store. So that's what that Post-it note is modeled by this little notation down here, where the customers will be represented as this tuple, where the first thing is just C. The C doesn't matter. It's just a reminder to us that that's a customer. The customer's ID, and that's just a number that we're just going to increase for every customer. So that's the same as I have up here. And then comma, their arrival time. So at the instant they arrive, I create a customer record. that has these, that where their ID will be one more than the previous customer, and their arrival time will be whenever they currently arrive. So the first customer's record will look like this because they arrive at time 0. So we'll see where that comes in a second here. So the checkout line is that state variable that keeps track of who's waiting at the moment. And we're kind of bundle the customers in the service as well as the customers in line together in one structure we're calling checkout line. So our checkout line is just going to be a list of customers like this one down here, where this customer is the one being served and these two customers are waiting. So we see a customer 2 arrived at time 1 and is currently in the server. Customer 3 is waiting to get in the server. They arrived at time 2. Customer 4 is waiting to get in the server. They arrived at time 8. And so here I can see that the length of this list will be LS1 plus LQ2. So this sum, LQ plus LF, should always be the length of the checkout line. That's something that will be the true case in every line of your hand simulation. And so we'll see in a second when we generate this table, that'll be a little clear, and then I'll ask for questions as we generate the table. So there are 3 types of events in this simple hand simulation system. There's an end event, an arrival event, and a departure event. So the each of the events is itself a little record that carries with it its own little post-it note with information. And so the end event, you have to bundle with the end event the end of the simulation. So each one of them is going to have a time of the event. So the end event, all we care about is the time of that event. That's when we schedule it. The arrival event is scheduled at time t, but then it has this extra piece of information, who arrived then. So that's just for our use. As we're processing these events, we need to know, okay, I've hit this event. What other data do I need to know that happened at this event in order for me to move forward to my simulation logic? Well, I need to know who arrived at that event. And then likewise, the departure, if that's in my event calendar and I hit that departure, at that point, I need to know who departed. And that's this extra piece of information here. So those are each called event notices. In our future event list or event calendar in, so Arena, they might call it an event calendar. In MATLAB, I think they might call it a schedule. So yeah, by the way, MATLAB also is another tool that has a discrete event system simulator inside it. And then in our textbook, they call it a future event list, FEL. So, but they're all sort of the same. So at any instant of time, at this instant of time, we have 3 events ahead of us. The end event, which is always going to be there until the end of the sim. There's a departure event of customer 3 at time 11, and there's an arrival event already scheduled at time 15 of customer 5. So that's how we would read that there. Okay. Yeah, and that's kind of what's being represented here. Okay, so what's the logic? And so we're going to go through the logic of those 3 events, and then we're going to generate the table, just like you're going to generate in the homework. I have an additional video. If you go to the homework assignment, down at the bottom, there's a bunch of other resources. There's a PDF where I've basically taken the solutions for this homework, for this hand simulation for like the last 5 years, and just put them into one document. So you have extra practice there. You can see those solutions to kind of check your intuition. And I also have videos where I do these processes, so you can watch that. So look for those extra resources. And then, that's also what I'm doing here. So whenever we hit an arrival event as the next event in the event calendar, we go through a set of steps. This is just a recipe that you follow. And if you follow this recipe precisely, the hand simulation just unrolls naturally. So if the next arrival event I'm processing is an arrival event, I read this record as saying at time t, so that's the current time, customer I arrived. And so then the customer I's record, which is they're going to be in the checkout line, if I look at them, then the time associated with them is when they arrived. And so I'm going to need to create that record, and since I know their arrival time, and put them in the checkout line. So if the checkout line is empty, so these 2 things sum to 0, which can happen if the server is idle, then this arrival goes directly into the server. So how do we do that? Well, there's 2 things we do to put the customer in the server. we schedule their departure event. So we look up at this customer and we look down at their service duration, and we're going to add their service duration to the current time. That will be when they depart. And then we're going to create this departure event. We put D, so we remember it's a departure event. We put that sum that I just talked about, current time plus the service time from the table. And then we tag it with the current customer's ID. So we remember that this customer, 6, 5, whatever, is the one departing. The other thing we have to do is, because there wasn't anyone in the server and now there is, we need to add 1 to LS, which basically means take it from 0 idle to 1 busy. Otherwise, if the checkout line is not empty, then that means the server is being used. At that point, we can do a lot less. And so the customer has to wait. So we're going to increase the LQ state variable by 1, the number of customers waiting. And that's pretty much all we can do with this customer, because we don't know when they'll actually get into that server. And then we always put the customer in the checkout line, and we always schedule the next arrival. And how do we get the next arrival? We just go to whatever the next interarrival duration is, add that to the current time, and then put this new arrival record into the future event list, and then process the next event from the future event list. Now, when we process the next event from the future event list, any questions about this? This will become much clearer when I actually start populating a table, but so far, any glaring questions about this? Okay, now if I instead, the first thing on the future event list was a departure event, then we would look at this departure event. It would have this record, the time of the departure, the customer who departed, and we could look in the checkout line to find that customer and whenever they arrived. And so what do we always do? Well, if there was a departure, we increase the number of departures. We keep track at the cumulative statistic. We know someone else departed, so we add 1 to the number of departures. Similarly, we add the response time to this cumulative S statistic, this sum here. We calculate the response time by taking the current time, T, minus the arrival time, which is that Post-it note that we stuck on the customer when they came in the system. And so that's the total time this customer is in the system being added to the previous sum, where this thing started at 0 at the beginning of the sim. Then, now the customer's gone, we can remove them from the checkout line. So we just take them out of that list. And then we can also decrease the number of customers in the server. Now, at this event, though, there's an opportunity for someone to then immediately start getting back into the server. And so in that case, even though we just decreased this service here, if there's someone that is currently in the checkout line, we're going to nullify that by increasing it again. So, of course, you don't have to show you doing both of these steps. That will just sort of happen, that these will kind of cancel out. But so if there's a customer waiting in the checkout line, you just move them into the server by making sure your LS stays equal to 1, and then decreasing the number of customers in the queue. And then the other thing is, now that they've entered the server, you can go up to the service durations, figure out how long they're going to be in the server, add that to the current time, which is T, and then schedule this departure event by placing this record onto the future event list. And then this customer is the next customer in the checkout line, and the service. So I mean, this is just reading off that, like, in the checkout line, this should be the head customer in that checkout line. So those are the events that I do on departure. And then the last thing I could process is the end event. So if the next event in the future event list, so I go and I start running this, is the end event, then I pretty much just terminate. So there might be other statistical things I might do. I might divide ND by S to generate some other stat, or divide S by ND to get some average stat or whatever. But for the hand simulation, for the homework, you just end. And so what does that look like? So this is the type of table you'll be generating in that homework. So we're just going to step through. We know that the first thing we do is, if I've told you to simulate it for 15 time units, it's not 15 in the homework. Again, like 21 or 22 or whatever, it's some number. Then the first thing you do is put the end event in the future event list. And so this column down here will be for every row. Every row will be the time of an event. And at any event time, there will be a future event list that lists all of the events that we know will happen in the future. And so at time 0, so this will eventually have a 0 here, we know that there will be an event in the future in 15 minutes or whatever, that will be the end time. Then the first thing that we do is schedule that arrival event. So we know that the first customer arrived at time 0. So customer 1 arrives at time 0. And so we're not actually going to put them in the future event list because we're sort of processing that event right now. So pretend like you just pulled that out of the future event list and then unroll through that logic that I just talked about. So for an arrival event, the first thing we do is we set the clock to the time of that in that event record. So we're going to set it equal to 0. And then we have to say, okay, what is the things that happen to customer 1 once they've arrived? Well, they arrived to an empty checkout line. So that means they're going to get in the server. So we can go up here and notice I put it in red here. Customer 1 spends a minute in the server. So we are going to add 1 to the current time and then create a departure event that is 1, which is just 0 plus that service time of customer 1. And we're going to put it in the future event list in order. That's really important, that this future event list should always be ordered by this middle number. So 1 before 15. Don't put it after the end event. It always has to be listed in order because this first event is going to dictate the time of the next row. After that, then we increase this state variable from 0 to 1. That's the number that are in the server. And then we put customer 1 in this state variable, the checkout line, which shows all of the customers in the system. And then we schedule the next arrival. So we can look up here at this table and we say there's 4 minutes in between customer 1 and customer 2. So we're going to add 4 to the current time, which is 0, generate an arrival record, A4 of customer 2, and then that will go there in our future event list. And that basically fills out the table because there's nothing that happened that would have caused the F to change or the ND to change. And LQ just takes its initial value of 0. And that is all that we're done with here. And so our next step will be to grab this event and populate the next row. But before I do that, were there any questions about how I generated this row? Yeah. Yes, so these are sorted. Great question. These are sorted by this middle time. So notice it goes 1, 4, 15. So when you add an event record, make sure you add it in order of that time. So if I were to go back before this, it all started out with 15 as the lead. And then I added an event record, and the first event I added was 1. 1's before 15, so I'm going to put it at the head of the list. But then the next event that I needed to grab had a time of 4, so I'm going to put it in the middle of the list. So these are always going to be sorted by that middle number. Yeah. Great question. Yes. So in this case, it's hard because of the 1, but theoretically, if the departure happened at 14, like if I would have just changed these service and an arrival durations, you could change these numbers so that the arrival would have an arrival time before the departure time. And that absolutely could happen in the real system. And then the poor customer that arrived early would just have to wait. So this is set up so that when customer 2 arrives, they won't have to wait because customer 1 will already be departed. But these could be switched, in which case when we process the arrival event next, then customer 2 would just have to sit there and wait. Does that make sense? Other questions? All right, great. Well, let's process the next row then. So we're going to grab this first event in the future event list by jumping to that point, and that will be the next time that we simulate. So we jump, and we're processing this event record now. It's a departure event. So what do we do on a departure event? Well, first thing we do is we add 1 to the number of departures because we just got a departure. The second thing we're going to do is calculate how long that customer, which in this case is customer 1, spent in the system. Well, if I look at my checkout line, customer 1 entered the system at time 0. It is currently time 1. So they spent 1 minus 0. That's how long they spent in the system. So I'm going to add this response time to the current sum of response times, and also that will become a 1. And then I'm going to remove that customer from the checkout line because they're not in the system anymore. So I'm going to just empty that checkout line. I'm going to remove them from the server. So the server is going to become idle. And then I'm going to update my clock and write down everything that I just did. So this event here, this shows that we've processed this event. That's why it isn't in the future event list anymore. The other two events are, and we haven't scheduled any new events because we typically, the only time we schedule an event on a departure is if there's a customer that was waiting to get into the server. There were no customers waiting, so we had nothing to schedule. So the event list just got smaller. So any questions on how I got that row? Okay, well, let's do it, a couple more rows here. So we're going to jump to the next event in the future event list, which is the first one. So wherever a current row is, it's the first one on the event list in that row. And that happens at time 4. And it is an arrival event of customer 2. So now we're going to go through the arrival logic. Well, what do we do on arrivals? Well, in this case, customer 2 arrived to an empty server. So we immediately can schedule their service. So customer 2 arrives at time 4. They spend 8 minutes in the server. So we're going to add 8 to 4 to give us the 12 here for this departure event that we're going to schedule, which will show up on the future event list for this row when we're done with our processing. So that departure 12, that 12 comes from 4 plus the 8 in the table. So then we have to add 1. So at this time 4 that we're processing, we're going to add 1 to the server. The server is now busy. We are going to add this new customer to the checkout line, which was previously empty. And then because we processed the arrival, then we need to schedule the next arrival, or else our sim will just, will stop eventually, it'll stall out. So we look up at our interarrival durations, and after customer 2, there's 2 minutes before customer 3 arrives. So we're going to add 2 to the current time 4. 4 plus 2 gives me 6, and that's our new arrival event. So we added this departure event and this arrival event to the list. So then I get my full table. So at time 4, this is what my checkout line looks like. This is what my FEL looks like, and that's everything else. So any questions about that? All right, well, then what's left there is what happens when someone arrives when the server is busy. And fortunately, that's exactly the state we're in here. So we can do that example here. So we now have a server that's busy, and the next event we have to process is an arrival event. So we're going to jump to time 6. Time 6 right there, that arrival event. And then we have to figure out what's the logic of a customer who's arrived while the server is busy. Well, we have to add 1 to the queue. We have to say that there's going to be a customer who's waiting. So we don't add 1 to the service state variable. We add 1 to the queue state variable, the length of the queue variable. We then also put them directly in the checkout line, but because they're not the first in the checkout line, they're not the one being served. They're just the first one that's waiting. And then we schedule the next arrival. So we look at the list here, and after customer 3, there's a 1-minute wait until customer 4 arrives. So then we can schedule 4. So really the only thing that we're doing in this is we're getting rid of this arrival event and adding a new arrival event and putting that customer in the waiting line. And that's what we see here. So at time 6, now we've got 1 in the queue, 1 in the server. We've added the 1 in the queue to the checkout line. We've swapped arrivals here. And now customer 4 is in the same position as customer 3 was in. They've arrived and the server's busy. So we do the same thing again. We jump to that. We add 1 to the queue. We put them in the checkout line. We schedule the next arrival, which in this case is going to be after the end time. So you're going to be tempted to say, oh, the arrival happens after the end time, I'm not going to schedule it. Do schedule it, because when the computer is doing this sim, it's got thousands of these events potentially at the same time. It doesn't look ahead and search for the end time and then stop scheduling. It just adds things to this list and processes the next thing in the list. So even though the next arrival, so where do we get that arrival? Well, this customer after customer 4, there was a 9-minute wait before customer 5. So the arrival of customer 5 happens 9 plus 7, 16, which happens to be after the end time. So we're going to put that in the future event list after the end time, and that's what we see here. So that's a totally reasonable thing to have there, is have events after the ending events, because they're all sorted by that middle time. And I could keep doing this. So so that, you know, there's going to be a departure. And so I'm just, we've already gone through that logic. So I just want to populate this whole table here and to show you that since we just processed a departure of customer 2, we got the departure timer went up. We got the response time variable went up by the 8 minutes the customer 2 spent in the system. And then we would process this departure event again. And so we have now this C3 departed, and now we have this end time, which is our first event. And so I think I tell you at the top of the homework that you don't have to include the end event. So we theoretically could then copy this row down without the end event, but that would kind of be silly to do. And so it's okay to just have the last line of your sim be a row of the simulation where the first event in the future event list is the end event, and then we're done. So questions on that table? So you just follow the recipe, different logic for different events, and different logic for different events and different state variables. So the logic is conditional based on the state of the system. And that's what is really the magic of simulation, is that these response times depend on the state of the system, whether a customer is already in the server when a new customer arrives. It's very hard to know that without running the sim. We run the sim, and then we can then divide 16 by 3, and that gives us our average time in the system for each one of our customers. And we can decide whether we think that, you know, almost 6 minutes in the system is a good average for these customers. Okay, so we jumped our end event and we're done. Okay. I'm going to skip that one, theoretically. Actually, yeah, I thought I had more for you. Actually, I'm not going to skip that one. I never end on time, let alone early, as you might have sensed. So let's not skip that one. Let's do that iClicker then. Let me go and stop the other poll and start a new short answer poll. So for this one, then tell me how many arrival events should be in your future event list at any time. So if you're doing our hand simulation of the MM1Q, like you're doing in the homework, how many, I'm looking for a number, 0, 1, 2, 3, 4, how many arrival events should be in your future event list at every time? So what is a pattern that we are sure about, that the FEL will always have this number of arrival events in it? And then that's all I've got for you. So I'm happy to take questions if there are any questions. Otherwise, we'll see the spreadsheet version of this next time, which is that extra credit version. So try it on your own. But then otherwise on Tuesday, I'll show you how to do this in a spreadsheet as we kind of move closer and closer to computational models to get this stuff done.